All right, this is one of the applications for Avogadro's law. That is, if the temperature and pressure are constant, that is, they don't change from going from reactants to products, then we can just use the volume ratios in place of the mole ratios. So it's a 2-to-1 mole ratio, and there'll be a 2-to-1 volume ratio. And then if we know the molar volume at STP, then we can figure out the volume ratios in STP on a mole basis. STP is not that useful. So what's more useful is RT. RT stands for room temperature, and room temperature is what? Yeah, they're 25 degrees Celsius in 1 atmosphere. 1 atmosphere is normal atmospheric pressure. It's close to a bar. And so I have it memorized to 4 sigma. Room temperature in 1 atmosphere, a liter of any gas, ideal gas, is 24.45. A mole, excuse me, not a liter, a mole of any gas is 24.45 liters. That's for an ideal gas. You know, it varies a little bit for real gases, but we'll just go with that. So oxygen and hydrogen are fairly ideal. Hydrogen is more ideal. And we'll ignore it right now. Deviations from ideal. We'll just say, okay, mole of gas is 24.45 liters. 2 moles of gas is 40. And that's going to form 2 moles of water. If this is gaseous water at the same temperature and pressure, then we can just say 48.9. So this is a very fast way to do stoichiometry. We usually do volume ratios like this. We do stoichiometry. But sometimes you want to do something like this for quick calculations. So one variation of this is rather than forming H2O gas, we form H2O liquid. So let me put that in here. So if we take 48.90 liters of hydrogen at RT 1 atmosphere, and 24.45 liters of oxygen at RT 1 atmosphere, and that's 2 moles of hydrogen, 1 mole of oxygen, and the mole ratio is always correct. We form 2 moles of water. But would this 2 moles of water occupy the same volume as this 2 moles of water? Do you think? No. These 2 moles are gaseous water, and this is liquid water. And so, in this particular case, a mole of water weighs 18.06 grams, so 2 moles of water is going to be 36.04 grams of H2O liquid. That's 2 moles of H2O liquid. And what's the volume of that? The volume of this is going to be 36.04 milliliters of H2O liquid, which is going to be 0.03604 liters of H2O liquid. And so I did this using the molar volume so I could quickly calculate, the volume of liquid water. The volume of liquid water is going to be 0.036 liters and not 48.90 liters. It's all going to condense into phase. Did I talk about these molar volumes already, or not yet? This molar volume I had to memorize at 3/6 when I was taking chemistry. And I still remember 1 mole of gas is 22.4 liters at STP. STP used to be this. This is what we'll call the old STP. And so this is the STP I memorized as a student. And the old STP is 0 degrees C and 1 atmosphere pressure. 1 atmosphere is fine. That seems pretty standard because that's normal atmospheric pressure. However, 0 degrees C is not normal room temperature, is it? I mean, it's too cold. And so there's lots of data tables with data at STP, and it's just comparing things like volume and whatnot. But I didn't find it that useful because I didn't do much at 0 degrees C.
Are we going to use that definition of STP or a different one?
No, now you have to learn this definition of STP. And the difference between the new one and the old one is the pressure. It's still at standard temperature, which is 0 degrees C, but standard pressure now is 1 bar. And so I'm sure students are memorizing it as 22.7 liters per mole. But when the time when we use this most is in stoichiometry. Most of the stoichiometry problems are going to be at room temperature. Unless it's focused just on STP calculations, then you might see an unusual bias towards STP. But since most of them are at room temperature, and most of them are going to be at 1 atmosphere, this isn't as useful. And so I wouldn't bother memorizing either of those. If you're going to memorize one, you don't have to memorize this because it's easy to calculate. 1 mole of gas is equal to 24.45 liters of gas at 25 degrees C and 1 atmosphere. This might save you some time in calculations. But it's if you forget, it's a fairly easy calculation to do. It doesn't take very much time. And so we have a bunch of these boxes here. You can buy boxes that are 22.4 liters of volume. And so I have a box over there that will bring it out. It's 22.4 liters. It's not a mole worth of gas. In other words, 6.022 comes in the 23rd gas particles inside the box. The identity of the gas doesn't really matter.
Like a mole of gas next to a mole of liquid is like so different.
Yeah, it's a huge difference.
Roughly by what factors? Roughly.
You can take a look. About 1,000, more than 1,000. Yeah, because it's 48.9 liters, and this would be 1,000, more than 1,000 times smaller. So there's a lot of empty space in the gas. When the liquid collapses, then you lose a lot of empty space. There's still a little bit of empty space in the liquid. The molecules are touching one another, and so you can't really compress them closer. So we can take these laws, the Charles law, Boyle's law, and Avogadro's law, and combine them into the ideal gas law. So I'm going to skip this and we just go here. So this is ideal gas law, P equals nRT, or PV over NT is equal to constant R. And the constant R depends on what units you use. I only memorize 1 or 2 R values, probably 2 R values. You only need to know 1 R value, but because you can derive all the others based on it. And so I just remember this one, 0.082057338. I don't memorize it to this many sig figs. I just memorize this to 4 sig figs. And to 4 sig figs, what is that? R value. 0.08206. We just rounded to 468. So this is our R value here. If I'm given bars, I'll just convert bars to atmosphere. There's 1.01325 bars in an atmosphere. So if I know that conversion factor, I can do that. In Chem 4, he really liked torr, and so it's like 66.4. But it's not useful to memorize all the R values. The best thing is just to memorize this one here. And maybe this one here. This one's a good one to memorize as well. 8.31445. I usually do this one to 5 sig figs. I'm not sure why. You could do it to 4 sig figs. 8.314 or 8.3145.
Digit away from getting pi. It's a digit away from containing pi. 3.9445.
Yeah.
That would be sweet.
But it's over. 8.314 is probably fine. And that's in joules per mole Kelvin. If I'm given bar, or if I'm given pascals or kilopascals, I'll just do the conversion. If you take a look at these two, though, Pascal per cubic meter, mole Kelvin, this is in SI units here. And so this is SI units, this is joules. Joules is derived from it. So applying the ideal gas equation, we use it to calculate different things. So I can calculate the volume here for 1 mole of gas at room temperature and 1 atmosphere. And the volume is equal to nRT over P. N is just 1 mole. R is 0.08206 liters times atmosphere per mole Kelvin. T is going to be 298 Kelvin. P is just 1 atmosphere. Actually, let me go 298.2 Kelvin to get one more digit. 298.2 or 298.15. And so I'll do this here. That's 0.08206 times 298. I'll just do 15. Actually, comes out a little higher. 24.466 liters is 24.47 liters. So I'll have to rememorize this. 24.47. If I do 298, what does it come out to? 0.08206. Where did I get 24.45 times 298? And 24.45. Or 24.5 or 25 liters, depending on how many sig figs you want. So I need to adjust my previous calculation. So the 4 sig figs, 24.47, the 3 sig figs, 24.5, and the 2 sig figs, 25. Sometimes all you need is 2 sig figs. Based on the calculation, we don't have to be that precise. And so it's a bit easier if we just round it to 25. And those are okay for more qualitative calculations. Oftentimes in multiple choice, you can do qualitative calculations. You don't have to be so precise. So you take 50 liters plus 25 liters, should give you 50 liters of gas. And that gets you close enough. This is called the molar volume. And what we can do is we can just say it's 25 liters per mole of gas. Alternatively, we can calculate it like this. The molar volume is the volume per mole, so it's V over N. When we do V over N, that's just equal to what's left over, RT and P. This is equal to the molar volume. And the units for the molar volume are going to be in liters per mole. So we could repeat the same calculation and we get, 24.47 liters per mole. Just like plugging in R, T, and P. Calculating the molar volume is very useful for stoichiometry. And so,
Can we take class notes in our lab notebook or no?
Do you what?
Take class notes in our lab notebook.
You could put whatever you want in your lab notebook. It doesn't matter. P equals molar volume. So this is, again, for stoichiometry. And we use this as a stoichiometric conversion factor. So that's one application. There are multiple applications that we can do. We have the molar mass determination. I derive the molar mass differently here. I just go molar mass is equal to, this would be an alternate derivation. Molar mass is equal to the mass over moles. So mass is in grams, N is in moles. So this is grams per mole. And then I know that N is equal to PV over RT. So I'll substitute it. So I'll get the molar mass is equal to the mass over PV over RT, which is equal to the mass times RT over PV. This is the molar mass, or this kind of M here, symbol that they use.
What is that?
PV.
No, in that RT.
This RT here or this RT?
That RT, like the one I put on. What is that?
This thing here?
Yeah.
Substitute. It's supposed to say substitute.
Oh.
For N. So this is the equation here. In other words, the mass, molar mass is equal to the mass times RT over PV. We can get additional relationships too. So for example, mass over volume
is equal to the density. So mass divided by volume is equal to the density. So what we could say is this is equal to the density times RT over P. Or we could solve for density here. The density is equal to the molar mass times P divided by RT. Or we could do an alternate derivation for density. Let me take a look. The alternate derivation, density is given as delta here rather than D. I don't know. Yeah, it's all mixed up. The symbols that people use.
So it's uppercase, lowercase, and now Greek D?
Yeah, uppercase D, lowercase d, and now, yeah, Greek, right?
D is one. I mean, shout out to D. D is always kind of filtered, except when it's velocity.
I don't know what they're going to do next, but this is it. Oh, there's one more. Sorry. For density, do you know the other symbol for density?
Oh, yes, it's not like Greek or
It's Greek, actually.
it is.
Yeah. Let's see if you know this one. You know that one?
P?
No, not P. That's supposed to be rho, but anyway. There's lots of different symbols that they use. But what we can do is we can substitute V. V is equal to nRT over P. So this would be an alternate derivation here. We'll do that up here. And so I could use delta, which is equal to D, which is equal to rho, which is equal to density. So I'll go with our books. Delta is the mass over volume. And then this is going to be mass over V is equal to nRT over P. And then invert and multiply. It's going to be the mass times P divided by nRT. And then the mass over moles is equal to the molar mass. So this is going to be the molar mass times P divided by RT. And so we have the same thing. Molar mass times P. This is supposed to be P divided by RT. These equations are the same as in Chem 4, correct? Yeah. This one's a little bit different. You remember this one? What was this equation called? Let's see what they call it. We can call it the combined gas law. But that's only if n is constant here. Really, we should have the Chem 1A version of the combined gas law. This is the Chem 1A version of the combined gas law, where the number of moles can change. So let's say you have a container and some gas leaks out of the container. Then you're starting off with more gas and ending up with less gas, moles gas. Or let's say you have a container and you inject more gas into it, then the number of moles changes. The reason why vapor pressure doesn't obey the ideal gas law is because the number of moles is continually changing with temperature. So as the number of moles change, that's going to alter. And so I shouldn't say it doesn't obey. I mean, it does obey if you continually adjust for the change in moles with temperature. So let's say you follow the temperature from 25 to 100 degrees C, and you have to compensate for additional moles of liquid that are going to be vaporized at 100 degrees Celsius, 25 degrees C. And if you can compensate for that, then you can model it. So gases and chemical reactions, let's take a look at the law of combining volumes, which is the Avogadro's and others. So I'm going to insert a slide here. So normally we do a moles of A to moles of B type conversion in stoichiometry using a mole ratio. But we can skip this mole to mole conversion and go directly from the volume of A gas to the volume of B gas by using the volume ratio. There are a couple of constraints for using the volume ratio. One, they must be gases. And the other constraint is that the pressure and temperature is constant. That is, it doesn't change. If they aren't gases, then we're going to have to do the mole-to-mole conversion. So for example, if B is a liquid, then we go from volume of A gas to mole. The easiest way to do that is you have two choices here. You could use the ideal gas law, or you can use the molar volume. Personally, I'd like to use the molar volume here. And that's why I like to memorize one molar volume, 24.5 or 24.47 liters per mole. And in fact, we have to flip this over because molar volume is in liters per mole, and so we want moles per liter, so I'll just invert it. Over here, we can just use the molar volume straight. That's liters. And so we'd have to do this stoichiometrically if the pressure and temperature change. So let's say the reactants were measured at one temperature and pressure, and the products were measured at a different temperature and pressure, then we'd go through this because the molar volumes change with temperature and pressure. So I'm going to figure it out. And the molar volume equation, I usually just memorize rather than derive, because it's pretty simple to memorize. And it's pretty simple to check your answer, RT over P, because the units have to be in liters per mole. And so you want to make sure everything cancels out to give you liters per mole. It's going to be the molar volume. This is good if B is a gas and A is a gas. Just do the volume to volume stoichiometric ratio. So we did an example of this with the hydrogen and oxygen reaction going to water. We have different ways of visualizing this. So in order to get this reaction in the correct stoichiometric ratio, I can just take one volume of oxygen and two volumes of hydrogen and mix it together. And so it could be like 1 liter of oxygen plus 2 liters of hydrogen, or it could be like 10 liters of oxygen. 10 liters of oxygen would require 20 liters of hydrogen. Or 1 gallon of oxygen would require 2 gallons of hydrogen. So we mix them into the one ratio. That's called an Avogadro's mixture. Avogadro. We have two ways that we visualize, actually 3 ways that we visualize mixtures. One way is visualizing by volumes. Another way of visualizing mixtures is by pressure. Let's say I just had a tank. I had a tank of oxygen. I need to put some hydrogen in there. I need to put twice as much hydrogen in there. And so what I'm going to do is I'm going to take the tank and then inject hydrogen into it. But let's say the tank is 25 liters. How am I going to inject 50 liters into a 25-liter tank? can I? Or how do I measure that out?
Put more pressure.
Yeah, you put more pressure. And so we have two ways of visualizing gas mixtures like this. If I have volumes, I'll just do volumes, which is Avogadro. If I have a tank, then let's say that I have a tank that has 1 atmosphere of oxygen in there. How many atmospheres of hydrogen should I put into the tank? 2 atmospheres. So if I have 1 atmosphere of oxygen and I inject 2 atmospheres of hydrogen, how many total atmospheres do I have? 3 atmospheres. This is a weird one because when I do this, if I take 2 liters and 1 liter, I'll get 3 liters of mixture. And then I'll let it react. And when those 3 liters of mixture react, then the volume shrinks back down to 2 liters. And so when we deal with gas mixtures, it can get a little confusing. So when I deal with gas mixtures, I usually look at this. This is called the mole fraction. And the mole fraction is always valid. And this is the pressure fraction. The pressure fraction, this is valid when we have constant volume. And this is the volume fraction. The volume fraction is valid with constant pressure. This is the symbol for the mole fraction. If we take the mole fraction and multiply it by 100%, we get the percentage. And so we can get the mole percent, the pressure percent, the volume percent here. And they're all the same. The mole percent is equal to the pressure percent, which is equal to the volume percent. And so let's take a look at an example of this here. Okay. This is the pressure fractions. This is called Dalton's mixture or Dalton's law. This is Avogadro's mix or Avogadro's law.
There's Dalton's law for pressure, Dalton's pressure the same thing.
Yeah, Dalton's law and Dalton's mixture is the same thing. Dalton's law is a mathematical equation describing the Dalton's mixture. This is different than, this is just mixing these two things together. When I take 5 liters of hydrogen and add 5 liters of helium to it, how many liters should I get? 10 liters. That would be according to Avogadro's. So we would get 10 liters. But there's a problem with that because when we look at the pressure,
here, it's 2.4 atmospheres, this is 6 atmospheres. And then we wouldn't treat it the same. Avogadro's would be different. This is what we call Dalton's mixture here. And then we'd have to further analyze this to get an Avogadro's mixture. So this is Dalton's. And so what you should be able to do is you should be able to switch back and forth from Dalton's to Avogadro's. Okay, so here, Dalton's, the pressure of the hydrogen, you know, in other words, the pressure fraction is equal to the pressure of A over P total. So that would be the pressure fraction of A. The mole fraction would be the moles of A over moles total. So let's go ahead and calculate the mole fraction first. The mole fraction is going to equal 0.50 moles of hydrogen over 1.75 moles total. And so our our mole fraction is 0.50 over 1.75. We can simplify that. Let's go ahead and do that here. So I got 0.5 divided by 1.75 is 0.2857. So I'm only allowed 2 sig figs here, but I'll go extra. 0.2857 over 1, which is going to give me 28.57% by mole. This is 28.57% by mole hydrogen. If we calculate the pressure fraction of hydrogen, it's going to be the pressure of hydrogen, 2.4 atmospheres, divided by the total pressure. The total pressure is over here, 8.4 atmospheres in the mixture. And so the fraction is 2.4 divided by 8.4, which is equal to 2.4 divided by 8.4, which is equal to 0.2857 over 1, or it's 28.57% by pressure hydrogen. So this mixture over here is 28.57% hydrogen, the blue one by mole, and it's 28.57% hydrogen by pressure. Because the pressure that's going to be generated by the blue molecules hitting the wall is 2.4 atmospheres. So over here in the mixture, we have the same number of blue, and so we'll generate the same pressure. 2.4 atmospheres worth of the pressure in the mixture is going to be generated by the blue fluid. And the rest, since there are only 2 things in this mixture, the rest has to be helium. And so it's got to be 71.43%. 71.43% helium. So in other words, 71.43% of the total pressure, 71.43% of 8.4 atmospheres is 6 atmospheres. And so the pressure that's generated just by the helium colliding with the walls is 6 atmospheres. Okay. And that would be the same for the mole fraction. It would be 71.43% by mole helium.
There's the hydrogen, the mole to pressure ratio is 1:1. Is that because of this hydrogen or because of STP?
1:1, where do you see 1:1?
The percentage of mole and actual percentage lengths.
They're always the same. That is, in other words, the pressure fraction is equal to the mole fraction, which is equal to the
volume fraction. But when you look at the volume, it's 5 liters of hydrogen and 5 liters of helium. So is the hydrogen still 28.57% by volume? Here. The answer is actually no. Because in Dalton's, what has to happen with the volume? In Dalton's, the volume is a constant. And so this is why when you take 5 liters plus 5 liters, you get 5 liters. And so the volume is constant. Everything has a volume of 5 liters. The hydrogen has a volume of 5 liters, the helium has 5 liters of volume, and the mixture has 5 liters of volume. And so what we say is constant 5.0 liters. Go ahead, yeah. All right, now we're going to switch to Avogadro's. So the mole fraction doesn't change. The mole fraction is the same as it was before, which was 28.53%. 28.53% by mole hydrogen and 71.47% by mole helium. And so what is the volume fraction of hydrogen? So the mole percent or the mole fraction is equal to the volume percent or the volume fraction. And so I have 5.0 liters. And so I want to know the volume of hydrogen. The volume of hydrogen is going to equal the volume fraction of hydrogen. The volume fraction is going to be 28.53 out of 100 will be hydrogen, and that's 5.0 liters. 1.428 liters. So I'm going to have 1.428 liters of hydrogen gas, plus the volume fraction of helium. Helium is monatomic. Which will be the balance, or we could calculate it. The volume of helium will be the volume fraction, which is going to be 71.47 out of 100 of 5 liters. It's 3.571. Is that going to add up? Yeah, 3.572. We'll just do 3.572 liters of helium. I should have written this up there. So V total is equal to the volume fractions, VA plus VB, the partial volumes plus ... So this is just going to equal the volume of hydrogen plus the volume of helium, which is this plus this is going to give us 5.0 liters. Here. Now, why did the volume shrink? Originally, I had 5 liters of hydrogen. Why did it shrink? You know why it shrunk? Yeah, we need to increase the pressure. We need to make sure under Avogadro's that all the pressures are the same. So if the mixture is at 8.4 atmospheres, then I need 8.4 atmospheres of hydrogen, and I need 8.4 atmospheres of helium. So if I take 8.4 atmospheres of hydrogen plus 8.4 atmospheres of helium, do I get 16.8 atmospheres of mixture? No, I get 8.4 atmospheres of mixture. And so, in other words, I'm just combining the volumes. I'm not compressing the gases into the same container. And so I'll just stack this on top of this, and then the total volume is back to 5 liters. But what we have is we have the same density of hydrogen over here. I mean, the same density of atoms, particles here. So we need to maintain that same density here to get that 8.4 atmospheres. And so the volumes are added in here. And so the pressures stay the same, the volumes are added in. So when you have a gas mixture, you can either think of the gas mixture in terms of Daltons or in terms of Avogadro's. Let's take a look at another mixture. Here. We'll just call this air or something close to air. I'll keep the numbers simple too. Do you know what the composition of air is? How much? Actually, a little higher. Nitrogen should be a little bit higher, like 78%. And so air is mostly nitrogen, about 78%. But you know what? I'm going to keep it even simpler. And we'll make it 80%. And so I'm going to just say air is 80% nitrogen. And do you know what the percentage of oxygen in air is? It's like 21% oxygen, but we're going to keep the number simple. We'll just go with 20% oxygen. So regardless, this is based on mole or particles. You know, if I had 100 particles in there, 80 of the particles will be nitrogen, 20 of the particles will be oxygen. 100 particles. And then what we're going to do is we're going to visualize this mixture in 2 ways. First, we'll look at Daltons. So if I look at Daltons, how many liters of nitrogen do I have? No, 1 liter. So I have 1 liter of nitrogen. And I'm going to separate that from the oxygen. How many liters of oxygen do I have? I also have 1 liter of oxygen. So if I have 1 atmosphere of air, then I just separate the nitrogen from the oxygen, but I give them the same volume container.
So now I'm going to have fewer collisions here because I don't have the collisions with the oxygen now. And what's going to happen to the pressure?
It's going to decrease. Do you know what the new pressure is going to be? Well, we know what the pressure fraction is. The pressure fraction is the same as the mole fraction, right? And so if it's 80% is the mole fraction, then 80% of the total pressure will be nitrogen. And so this is going to be 0.8 atmospheres. All right. I have been on hold for a little bit. Let me take this, and then why don't you do Avogadro's here and complete this for both. See if you can complete the picture for both. Let's just do one thing really quick. Sorry. Oh my gosh. I was on hold for 2 hours. All right. Forget it. Wow, that's the second time. I just moved the phone and it just hangs up. All right. Well, why don't you continue this? How many atmospheres of nitrogen? 0.8 atmospheres. And then how many atmospheres of oxygen? 2. 0.2. This is for the California Tax Board. Okay, then going to Avogadro's.
You'd think they'd be quite motivated to speak with you.
It's easy to not think.
Okay, when we go to Avogadro's, what's the volume of nitrogen? Dalton's is the sum of the partial pressures is equal to P total. So what is the volume? The 0.8 liters of nitrogen. And then how many liters of oxygen do I have? In order to have the volumes additive like this, what has to be the pressure? What's the pressure of the nitrogen? 1 atm of nitrogen. And what's the pressure of the oxygen? 1 atm. And so Dalton's, we have to make sure we have constant volume, and Avogadro's has to be constant pressure. No. Avogadro's. Avogadro's is constant pressure. So do you see 1 atmosphere of air is equal to 1 atmosphere of nitrogen, which is equal to 1 atmosphere of oxygen? Whereas Dalton's, we have 1 liter of air is equal to 1 liter of nitrogen, which is equal to 1 liter of oxygen. Now, which one we use depends on the problem. Sometimes we use Dalton's, sometimes we use Avogadro's. So here, where is it? Here. There are 2 ways we could do this particular reaction. One way is we could do Avogadro's like this. The other way we could do it is Dalton's. How would we do this as a Dalton's reaction? Here. Just do this one more time. Okay, I'll give up for today.
I don't think the market tax is very bad, right?
I got behind on my taxes, so taxes are due. But this is my 3rd day. I've attempted to talk to somebody, but haven't been successful. So when we look at Avogadro's like this, we'll take these, and then what we're going to do is we're going to form 3 liters of mixture. And then when that 3 liters of mixture reacts, we end up forming 2 liters of product. This would be Avogadro's. If we do this under Dalton's, we'd set it up differently. Let's say what I do is I just take, let's say this is a 1 liter box here. So this is the question I asked earlier. So if I have 1 liter of oxygen, how many liters of hydrogen do I need to add to it under Dalton's? How many liters of hydrogen do I need to add to it? 1 liter. And so how am I going to do that? How am I going to do that? Well, there's 2 ways. I mean, practically speaking, I just take this and inject the hydrogen in there. So I'm taking this 2 liter container of hydrogen and making it 1 liter. What's going to happen to the pressure? It's going to double. So let's say the oxygen were at 1 atmosphere, and the oxygen's still at 1 atmosphere. But now the hydrogen is going to be at, this is going to be 1 liter of hydrogen at what pressure? At 2 atmospheres. And so the total pressure now is going to be 3 atmospheres. After reaction, then I'm going to drop back down to 2 atmospheres of product. because I'm going to have fewer particles here. And so over here I had these 6 plus these 3 here is 9. I go from 9 particles in this box here back down to 6 particles. The pressure drops back down to 2 atmospheres after reaction. And so this is just different ways of doing this reaction. One is you inject different amounts of pressure into the same container. The other is to add different volumes. So you take a balloon of hydrogen, which is twice as big as a balloon of oxygen, and then combine those 2 balloons and let them react. And so it depends on the problem, which way we handle the mixture. But we end up with the same answer at the end. Now, this is a very common gas mixture here. This gas mixture is when we collect gases over water. What happens is the gas bubbles through the water here and it becomes saturated with water vapor. And so this gas becomes contaminated with water vapor. So this slide is showing you a couple of different things. One, and this is a very common method of collecting gases. A lot of gases are insoluble in water, like CO2. CO2 will bubble out. Hydrogen will bubble out. However, other gases aren't so insoluble. So if you had ammonia gas, the problem with ammonia gas is it doesn't like to bubble out. Ammonia really loves water. And so ammonia will stay in the water. There are other gases. Hydrogen chloride gas loves water too. It will stay in the water. And so it doesn't really effervesce or bubble out. But an insoluble gas will. And so, whatever. If this is oxygen gas, and our oxygen gas is now contaminated with water. All right, so one of the things that we want to know is we want to know what the total pressure of this gas is here. One thing we'd like to know is what is the total pressure of the gas? And if I look at this, this is like a barometer or manometer. This is kind of like a manometer, but the manometer has vacuum up here. And so which weighs more, the atmosphere freezing on the outside of this flask, or the gas? Which weighs more? The gas weighs more, or the atmosphere weighs more? The atmosphere weighs more. You can see that based on the different levels here. So when we look at this, the pressure of the atmosphere is a lot more than the pressure of the gas. And that's what gives us the uneven levels here. Over here, what weighs more, the gas or the atmosphere? Well, actually, it looks like the gas, is the gas a little lower level? Yeah. It's hard to say. The gas looks like it's slightly lower level. If it's slightly lower than the liquid level out here, then the gas weighs more. It's pushing the surface down deeper than out here. But let's say they're even, and this is just some optical. If the levels are even, then what can we say about the pressure of the gas?
That they're equal?
That they're equal. And so if these two levels are even, do you remember doing this in the lab? This is called equalizing pressures. And we can equalize pressures here by getting the two liquid levels the same. Such that the pressure of the gas is equal to the pressure of the atmosphere, the barometric pressure. And so if the pressure of the gas is too low, you know what we can do? We can't do it for this because this is not deep enough. So what we can do is we can force this down lower. As we force this container down lower, it's forcing water up into the container. As it forces water up into the container, it compresses the gas. So pretty soon the gas pressure will be higher and higher until it matches. So we just push this down until this level matches this level.
If the pressure is too high, we can lower the pressure. Let's say the levels aren't matched here, and the gas pressure is lower down here. What we can do is we can lift out the container. If we lift out the container, it siphons water out and creates a vacuum here, which lowers the pressure. And then we can adjust the height so that the two levels are equal. Once the two levels are equal, then we know the pressure of the gas here is equal to the barometric pressure here.
Now, the pressure of this gas is not, it's not a pure gas. We call this the pressure of the wet gas. And so the pressure of the wet gas is equal to the barometric pressure once the levels have been equalized here. That is, you either force more water into the container or suck the water out of the container by moving it up and down. So what would be more convenient for this?
Let's say I know the volume of this. If I know the volume of this, then would it be easier to talk about volume fractions? That is, what percentage of this volume is due to the water vapor and what percentage of the volume is due to the gas? Or would it be easier to deal with pressure fractions? That is, if I have this volume, then what pressure is due to the gas and what pressure is due to the water vapor? What do you think will be easier? And what's easier, as it turns out, is to do it by pressure fraction. Because the way that saturation works, let's say you go into an indoor swimming pool. When you go into an indoor swimming pool, it's really humid inside, right? Because the air inside there is going to saturate with water vapor. But what if the room is bigger? If the room is bigger, then more water will evaporate to saturate the air. But will that change the pressure fraction? No, the volume fraction and the pressure fraction are going to be the same. So the pressure fraction is going to be the easiest for this because the pressure fraction doesn't depend on the volume. Whereas the volume fraction does. I mean, the volume itself does. I mean, the pressure, I shouldn't say the pressure fraction. I should say the pressure doesn't depend. So in other words, if we want to know how much water saturates the air or the gas, then we look it up in a table. The table is the table of water vapor pressure. So we just find the temperature. So at room temperature, 25 degrees C, we'll have an amount of water evaporate such that it generates a pressure of 23.78 millimeters of mercury. And so if the room increases, we got to just make sure we have enough water to saturate it and generate this pressure. So this is called 100% relative humidity at 25 degrees C. The humidity, 100%, it's called relative humidity because it changes. It's relative to temperature. So at low temperatures, you can't get as much water vapor in, so it's saturated at 12.79 at 15 degrees C. At higher temperatures, you can get more water vapor into the air. And so at 50 degrees C, it's saturated at 92.65. So it doesn't matter the size of the container, the pressure is always going to be the same. But when we look at the volume will be different. The volume is going to change depending on the size of the container. And so we have to be careful about that. And so so what we're going to do is we're going to get the barometric pressure. So we equalize the pressures. And then we measure the pressure of the dry gas. Is equal to the pressure of the wet gas, which is the same as the barometric pressure because we equalize the pressures, minus the pressure of the water vapor. So this is a standard calculation that we do whenever we collect gases over water. Whenever we collect gases over water, we have to figure out how much water contamination we're going to get in the gas. And then once we determine that based on the temperature, then we can subtract it using Dalton's law.
So this is one of the major applications of Dalton's law. Okay. We're going to come back to that. We're going to talk more about that when we get to, we're doing an experiment with that. But I'm going to move on to kinetic molecular theory of gases. This is kinetic molecular theory of ideal gases, because there are some things that are restricted to ideal behavior. This first statement here, particles are point masses in constant random straight line motion. Have you heard this word point masses before? In point masses, we treat each molecule or atom or particle as a point in space. So it doesn't matter, it could be a gigantic molecule, but we're going to just treat it just as a single point. And the weird thing is, these single points have no volume. And so in an ideal gas, let's say I have 1 liter here of gas. If it's ideal, then it's 1 liter of empty space. This is very wide. 1 liter of empty space. And that's because all the particles that make up the gas are point particles, and these points in space just don't have any volume. So, for real gas, then that 1 liter is equal to X liters of empty space plus Y liters of particle volume. It depends, if the particles are really small, like helium atoms are really small, then it's fairly ideal. But if the particles are big, like sulfur hexafluoride or even bigger ones, then it deviates more. So the bigger the particles, the more it deviates from ideal behavior, because ideal behavior, we have these point masses which don't occupy any volume. The molecules are separated by great distances and normal pressure. At normal pressures, there's huge distance. This is very high pressure here. But they are separated by great distances. Molecules collide only fleetingly, and most of the time are not colliding. Most of the time they're just traveling without collision through empty space.
Wait, even when they're really hot? Even when they're really hot?
Yeah, even when they're really hot. When they're hot, they're going to have more collisions. The collision frequency is going to go up, but it depends on the pressure. If the pressure is still 1 atmosphere, then, well, what great distances means is this. When it says are separated by great distances are like, 100 nanometers or a micron, because the atoms are so small. So we can calculate, if it's under high vacuum, then it can travel miles without hitting anything. And so it's great distances relative to the size of the particles themselves.
Do you mean like miles in track its motion back and forth, or miles in like a particle accelerator?
No, when you track its motion back and forth. Yeah. So the volume of the particle in ideal is close to 0. This is ideal. The second thing that makes an ideal gas ideal is this. The IMFs, intermolecular forces of attraction, are about 0. For ideal, the particle volume is 0. There's no volume. And then IMFs are 0. That is, the molecules are sticky. This is like two billiard balls colliding, like pool balls colliding. Versus, if we have sticky molecules, it would be like two soft clay balls colliding. Two soft clay balls colliding might just stick to one another.
What was it up there after particles in the field gas?
X liters of empty space plus Y liters of particle volume.
Yeah.
So we can look at some simulations. For ideal gases, there's only one type of motion. Do you know the type of motion? We have 3 types of motion. What are the 3 types of motion?
Vibrational, rotational, and translational.
Yeah, vibrational, rotational, and translational. We could see some of it, and this is not gases. This is liquid. Vibrating in ice. Unless we cool the ice to absolute 0. If we cool the ice to absolute 0, then there's no vibrational motion either.
Would we still call that ice?
At absolute 0? Yeah, it's still ice. There are different phases of ice, though. I mean, different ice structures.
Okay, this might take me thinking for like the top silliest question I've asked. If you dropped if an ice cube that was at absolute 0 appeared over a pool of room temperature water and it dropped in, would it like explode?
An ice cube at absolute 0 dropped
I
into,
can't say dropped because then it would fall through the air and it wouldn't be that cold anymore. But like
placed into,
immediately is placed into a pool of water.
would it explode?
Yeah, or implode.
Implode?
Something has to happen, right? There's no way it just would it freeze a lot of water around it?
Yeah, it would freeze a lot of water. I mean, there would be heat transfer. It would freeze it quickly. There could be like cracks and stuff. You would hear cracking, with mechanical stress. But I don't think it would implode. I've done liquid nitrogen into water. We can see it. When you pour liquid nitrogen through air, it just evaporates so fast. It just boils off. But that's an interesting question. I haven't thought about that, so I'm not sure.
Just use sodium.
Sodium you can make. Yeah, we'll do sodium tomorrow if you want to see. All right, let's take a look. So this is not ideal. Ideal gases. feel like he doesn't have any gravity. I think so. Maybe they use solar panels. But this is not very ideal. But one thing you notice is that are all the gas particles moving at the same speed? But you see that the gas particles, some are moving fast, some are moving slow. And what we have here is we have a distribution of energy. Now, ideal gas only has one type of energy. So, what kind of distribution do we have? A Maxwell voltage And so that means we have to speed up the slow ones and slow down the fast ones. If we speed up the slow ones and slow down the fast ones, what's the speed that they move or what energy do they move? And the speed that they move is called the speed. The effective speed for assuming all the water molecules. Let's say I don't like, having slow water molecules. Don't like having fast water molecules. All the water molecules to be the same, including yours. Kids are having time here. So the URMS is most important. Although we can calculate our and figure out the